Welcome to IMMYON Hyperworks online tutorial. In this first class we will be seeing some basics of FEM. So firstly, what is meant by FEM? FEM is known as finite element method. Finite means any continuous object has infinite degrees of freedom, and it is not possible to solve the problem in this format. So the finite element method reduces the degrees of freedom from infinite to finite, with the help of discretization or meshing, nodes and elements. Element means all of the calculations are made, at a limited number of points known as nodes. The entity joining nodes, and forming a specific shape, such as quadrilateral or triangular, is known as an element. To get the value of a variable, say displacement, anywhere in between the calculation points, an interpolation function, as per the shape of the element, is used. Method: there are three methods to solve any engineering problem. Finite element analysis belongs to numerical method category. Basics of finite element analysis. Analytical method. Classical approach. 100% accurate results. Closed form solution. Applicable only for simple problems like cantilever and simply supported beam, more. Complete in itself. So in a simple way, analytical method is a approach made by using different formulas, by which we get 100% accurate results. But takes lot of time to solve. Numerical method. Mathematical representation. Approximate, assumptions are made. Applicable even if a physical prototype is not available. Real-life complicated problems. FEM comes under numerical method. So, in a simple way, numerical method is an easy approach towards solving critical problems within less time with approximate results. Procedure for solving any analytical or numerical problem. There are two steps in solving analytical or numerical problems. Step 1. Writing of the governing equation problem definition, or in other words, formulating the problem in the form of a mathematical equation. Step 2. Mathematical solution of the governing equation. The final result is the summation of Step 1 and Step 2. The result will be 100% accurate when there is no approximation at either of the steps. Analytical method. Numerical methods make an approximation at Step 1 and at Step 2, therefore all the numerical methods are approximate. Below you can see the difference between the analytical approach and numerical approach. Experimental method. Actual measurement. Time-consuming and needs expensive setup. Applicable only if physical prototype is available. Results cannot be believed blindly, and a minimum of 3 to 5 prototypes must be tested. Brief introduction to different numerical methods. 1. Finite element method, FEM. FEM is the most popular numerical method. Applications: linear, nonlinear, buckling, thermal, dynamic and fatigue analysis. Are FEA and FEM different? Finite element method, FEM, and finite element analysis, FEA, both are one and the same. The term FEA is more popular in industries, while FEM is more popular at universities. Many times there is confusion between FEA, FEM, and one more similar but different term, FMEA, failure mode effect analysis. FEA/FEM is used by design or R&D departments only, while FMEA is applicable to all of the departments. 2. Boundary element method, BEM. This is a very powerful and efficient technique to solve acoustics or NVH problems. Just like the finite element method, it also requires nodes and elements, but as the name suggests, it only considers the outer boundary of the domain. So when the problem is of a volume, only the outer surfaces are considered. If the domain is of an area, then only the outer periphery is considered. This way it reduces the dimensionality of the problem by a degree of 1 and thus solving the problem faster. 3. Finite volume method, FVM. Most computational fluid dynamics (CFD) software is based on FVM. The unit volume is considered in finite volume method, similar to element in finite element analysis. Variable properties at the nodes include pressure, velocity, area, mass, etc. It is based on the Navier-Stokes equations, mass, momentum, and energy conservation equilibrium equations. 4. Finite difference method, FDM. Finite element and finite difference methods share many common things. In general, the finite difference method is described as a way to solve differential equation. It uses Taylor's series to convert a differential equation to an algebraic equation. In the conversion process, higher-order terms are neglected. It is used in combination with BEM or FVM to solve thermal and CFD coupled problems. Question: is it possible to use all of the methods listed above, FEA, BEA, FVM, FDM, to solve the same problem, for example, a cantilever problem? The answer is yes. But the difference is in the accuracy achieved, programming ease, and the time required to obtain the solution. When internal details are required, such as stresses inside the 3D object, BEM will lead to poor results, as it only considers the outer boundary, while FEM, FDM, or FVM are preferable. FVM has been used for solving stress problems, but it is well suited for computational fluid dynamics problems where conservation and equilibrium is quite natural. FDM has limitations with complicated geometry, assembly of different material components, and the combination of various types of elements, 1D, 2D, and 3D. For these types of problems, FEM is far ahead of its competitors. Why do we carry out meshing? The basic idea of FEA is to make calculations at only limited, finite, number of points and then interpolate the results for the entire domain, surface or volume. Any continuous object has infinite degrees of freedom, and it's just not possible to solve the problem in this format. Finite element method reduces the degrees of freedom from infinite to finite with the help of discretization or meshing, nodes and elements. FEM via numerical method. V mathematical representation of an actual problem. V approximate method. The finite element method only makes calculations at a limited, finite, number of points and then interpolates the results for the entire domain, surface or volume. You can observe in the first circle, it has infinite number of points which leads to high calculation time, but whereas in second one it has only 8 points, due to which the calculation time reduces. How the results are interpolated from a few calculation points? It is okay that FEA is making all the calculations at a limited number of points, but the question is, how it calculates values of the unknown, somewhere in between the calculation points. This is achieved by interpolation. Consider a 4-noded quadrilateral element as shown in the figure below. A QUAD4 element uses the following linear interpolation formula. U equals A0 plus A1x plus A2y plus A3xy. FEA calculates the values, at the outer nodes 1, 2, 3, 4, i.e. A0, A1, A2, A3 are known. The value of the variable anywhere in between could be easily determined just by specifying x and y coordinates in above equation. For an 8-noded quadrilateral, the following parabolic interpolation function is used. U equals A0 plus A1x plus A2y plus A3xy plus A4x2 plus A5y2 plus A6x2y plus A7xy2. What is DOF? Degree of freedom. In the example above, an object is fixed at one end, and a force is applied at the point P. Due to the force, the object deforms, and point P gets shifted to new position P. When can we say that we know the solution to above problem? If and only if we are able to define the deformed position of each and every particle completely. The minimum number of parameters, motion, coordinates, temp etc., required to define the position of any entity, completely in the space is known as a degree of freedom, DOF. Consider the following 2D, planar, problem. Suppose the origin is at the bottom left corner and is known. To define the position of point A completely with respect to the origin, we need two parameters i.e. x1 and y1, in other words two DOFs, translation x and y. Consider that the point A is a part of a line, now one angle should also be defined in addition to the two translations i.e. three DOFs, two translations and one rotation. Suppose points A and B are shifted out of the plane, and the line is rotated arbitrarily with respect to all of the three axes. The minimum number of parameters required to define the position of point A completely would be 6 DOFs, 3 translations, ux, uy, us, and 3 rotations, theta x, theta y, theta z. DOF is a very important concept. In FEA we use it for the individual calculation points. The total DOFs for a given mesh model is equal to the number of nodes multiplied by the number of DOF per node. Question: does all elements have 6 DOFs? All of the elements do not always have 6 DOFs per node. The number of DOFs depends on the type of element, 1D, 2D, 3D, the family of element, thin shell, plane stress, plane strain, membrane, etc., and the type of analysis. For example, for a structural analysis, a thin shell element has 6 DOF/node, displacement unknown, 3 translations and 3 rotations, while the same element when used for thermal analysis has single DOF/node, temperature unknown. For a new user, it is a bit confusing, but there is a lot of logical, engineering, and mathematical thinking behind assigning the specific number of DOFs to different element types and families. Question: how is the accuracy if we increase the number of calculation points, nodes and elements? In general, increasing the number of calculation points improves the accuracy. Suppose somebody gives you 3 straight lines, and asks you to best fit it in a circle, then find the area of the triangle, and compare it with the circle area. This is then repeated with 4, 6, 8, 16, 32 and 64 lines. By increasing the number of lines, the error margin reduces. The number of straight lines is equivalent to the number of elements in finite element analysis. The exact answer for the area of the circle, pi r2, is 100. 3 lines gives the answer of 41, while 4 lines gives 64, and so on. An answer of 41 or 64 is not at all acceptable, but 80 or 90 is considering the time spent and the relative design concept. Question: if a higher number of nodes and elements leads to a higher accuracy, then why not always create a very fine mesh with the maximum possible nodes and elements? The reason is because the solution time is directly proportional to DOF, and n can be 1 to 4, depending on the type of analyses and solver. Also, large size models are not easy to handle on computers, due to the graphics card memory limitations. The analyst has to maintain a fine balance between the desired level of accuracy and the element size, DOF, that can be handled satisfactorily, using the available hardware resources. Assume the analytical method approach gives answers very close to 100, and the time it takes is 1 month, while the finite element analysis with a reasonable mesh size gives an answer of 90 within 1 day. In industry, getting fast solutions with logical or reasonable accuracy is more important than absolute accuracy. That's why the analytical method approach is also known as the scientist's way to solve any problem, while the numerical method is the engineer's way to solve the problem. Types of elements. In the following table you can see different types of elements. Differences between 1D, 2D, 3D. Read it in order to get complete idea. Element shape characteristics in general. 4 shapes are possible: point, line, area, or volume. 1.A point element is typically defined by one node, such as a mass element. 2.A line element is typically represented by a line or arc connecting 2 or 3 nodes. Examples are beams, spars, pipes, and axisymmetric shells. 3. An area element has a triangular or quadrilateral shape and may be a 2D solid element or a shell element. 4. A volume element has a tetrahedral or brick shape and is usually a 3D solid element. Now, you can see in a clear way the representation 1D, 2D, 3D, how to decide the element type. A. Geometry, size and shape. For an analysis, the software needs all 3 dimensions defined. It cannot make calculations unless the geometry is defined completely, by meshing using nodes and elements. The geometry can be categorized as 1D, 2D, or 3D based on the dominant dimensions, and then the type of element is selected accordingly. 1D element, used for geometries having one of the dimensions that is very large in comparison to the other 2. The shape of the 1D element is a line. When the element is created by connecting 2 nodes, the software knows about only 1 out of the 3 dimensions. The remaining 2 dimensions, the area of the cross-section, must be defined by the user as additional input data and assigned to the respective elements. Practical example: long shaft, rod, beam, column, spot welding, bolted joints, pin joints, bearing modeling, etc. 2D element, used when 2 of the dimensions are very large in comparison to the third one. 2D meshing is carried out on a mid-surface of the part. 2D elements are planar, just like paper. By creating 2D elements, the software knows 2 out of the 3 required dimensions. The third dimension, thickness, has to be provided by the user as an additional input data. Why is 2D meshing carried out on a mid-surface? Mathematically, the element thickness specified by the user is assigned half on the element top, and half on the bottom side. Hence, in order to represent the geometry appropriately, it is necessary to extract the mid-surface, and then mesh on the mid-surface. Practical examples: all sheet metal parts, plastic components like instrument panels, etc. In general, 2D meshing is used for parts having a width/thickness ratio 20. Limitations of mid-surface and 2D meshing: 2D meshing would lead to a higher approximation if used for variable part thickness. Surfaces are not planar and have different features on 2 sides. 3D element, used when all the 3 dimensions are comparable. Practical examples: transmission casing, clutch housing, engine block, connecting rod, crankshaft, etc. B. Based on the type of analysis. Structural and fatigue analysis. Quad, hex elements are preferred over trias, tetras, and pentas. Crash and nonlinear analysis, priority to mesh flow lines and brick elements over tetrahedron. Mold flow analysis, triangular element are preferred over quadrilateral. Dynamic analysis, when the geometry is borderline between the classification of 2D and 3D. Geometry, 2D shell elements are preferred over 3D. This is because shell elements being less stiffer captures the mode shapes accurately and with a fewer number of nodes and elements. See time allotted for project. When time is not a constraint, the appropriate selection of elements, mesh flow lines, and a good mesh quality is recommended. Sometimes due to a very tight deadline, the analyst is forced to submit the report quickly. For such situations, 1. Automatic or batch meshing tools could be used instead of time-consuming but structured and good quality providing methods. 2. For 3D meshing, tetras are preferred over hexes. 3. if the assembly of several components is involved, then only the critical parts are meshed appropriately. Other parts are either coarse meshed, or represented approximately by 1D beams, springs, concentrated mass, etc. Can we solve same problem using 1D, 2D, and 3D elements? Is it not possible to use 3D elements for long slender beams, 1D geometry, for sheet metal parts, 2D geometry, and 2D shell elements for representing big casting parts? The same geometry could be modeled using 1D, 2D, or 3D elements. What matters is the number of elements and nodes, DOF, the accuracy of the results, and the time consumed in the analysis. For example, consider a cantilever beam with a dimension of 250 x 20 x 5 mm that is subjected to a 35 N force. You can see in the following figures, beam subjected to force. 1D beam model. 2D shell mesh. 3D tetra mesh. The values are shown in the table. How to decide element length. 1. Based on previous experience with a similar type of problem, successful correlation with experimental results. 2. Type of analysis. Linear static analysis could be easily carried out quickly with a large number of nodes and elements, but crash, nonlinear, CFD, or dynamic analysis takes a lot of time. Keeping control on the number of nodes and elements is necessary. 3. Hardware configuration, and graphics card capacity of the available computer. An experienced CAE engineer knows the limit of the nodes that can be satisfactorily handled with the given hardware configuration. Suppose you are a part of a newly formed CAE group, no clear guidelines are available, and there is no experienced person in the group, in the first run, accept the default element length. Mesh with the basic rules of thumb discussed in this book. Then run the analysis and observe the high stress regions. Remesh the localized areas of high stress, with smaller element length, and solve again. Compare the difference in the original, and the new results. Continue the process until convergence is achieved, 5 to 10% difference in strain energy / maximum stress value. Stiffness matrix derivation. What is stiffness and why do we need it in FEA? Stiffness K is defined as force / length, units N/mm. Physical interpretation: stiffness is equal to the force required to produce a unit displacement. The stiffness depends on the geometry as well as the material properties. Consider 3 rods of exactly the same geometrical dimensions: cast iron, mild steel, and aluminium. If we measure the force required to produce a 1 mm displacement, then the cast iron would require the maximum force, followed by steel and aluminium respectively, indicating KCI, KMS, KAL. Now consider 3 different cross-sectional rods of the same material. Again, the force required to produce a unit deformation will be different. Therefore, stiffness depends on the geometry as well as the material. Importance of the stiffness matrix for structural analysis. Stiffness is a very important property. The equation for linear static analysis is F equals Kd. The force is usually known, the displacement is unknown, and the stiffness is a characteristic property of the element. This means if we formulate the stiffness matrix for a given shape, like line, quadrilateral, or tetrahedron, then the analysis of any geometry could be performed by meshing it and then solving the equation F equals Kd. Methods for formulating the stiffness matrix: 1. Direct method. 2. Variational method. 3. Weighted residual method. The direct method is easy to understand but difficult to formulate using computer programming, while the variational and weighted residual methods are difficult to understand, but easy from a programming point of view. That's the reason why all software codes either use the variational or weighted residual method formulation. How to apply the correct boundary conditions? Who can teach us quickly? The application of boundary conditions is a tricky subject and is based on pure engineering judgment, skill, and common sense. No university, consultant, or book can teach these things. This is something to be learned from practical and field experience. 100% involvement, thinking about the behavior of the component due to various forces, and checking after every iteration whether the FE model is behaving in the same way as in reality. Displacement plots and strain gauge results for static analysis or natural frequencies and response comparison for dynamic analysis, etc. If the model is not behaving correctly, then modifications in the boundary conditions are needed. Discussions with experienced CAE engineers, field engineers, and testing department engineers are also needed. In short, making mistakes and reworking and modifying the FE model again and again until satisfactory correlation is achieved is the true teacher. Before going on with the software, let's see the formula we use in solving the problems in Hypermesh. For most of the linear static 1D analysis we can use the formula as M, H, P, C, L, L, where M equals material collector, H equals hyperbeam, P equals property collector, C equals component collector, L equals load collector, L equals load step. Thank you for watching the tutorial. In the next tutorial we will be working on 1D problems.